Good evening, and welcome to the Graduate Student Distinguished Visiting Lecture Series. My name is Dale Duran. I'm chair of the Atmospheric Sciences Department. We have a lot of people who will be speaking briefly before our main speaker, so I won't say much, but my main goal is to warn you that you are being recorded. The backs of your heads are being recorded, conceivably, and during the question and answer period, you'll be recorded too. So be aware of that. Beyond that, I should say that this series is enabled by generous donations to the Friends of Atmospheric Sciences Fund, especially from a few generous donors who prefer to remain anonymous. And the grad students organize it, have worked hard to make it happen, and they're going to take it from here. We have Clayton Sasaki and Sam Pennypacker.
All right. Thank you all so much for coming this evening. Welcome to the second Graduate Student Distinguished Visiting Lecture of 2019, presented by the graduate students of the Department of Atmospheric Sciences. My name is Sam Pennypacker.
I'm like Clayton Sasaki.
We are the coordinators for this year's events. This is the 15th year of the GSDVL program, and we are very grateful for the additional support that has made 2 visitors this year possible. The GSDVL is a unique opportunity for graduate students to be front and center, engaging with and learning from highly accomplished visiting scientists. In keeping with that focus, students get the first opportunity to meet with the lecturer and organize several meals with the speaker. This year's second GSDVL theme was atmospheric dynamics, and the graduate students enthusiastically selected Dr. Clara Desser, senior scientist and climate analysis division head at the National Center for Atmospheric Research, to be our distinguished lecturer. Dr. Desser joins the company of past speakers including Dr. Brian Hoskins, Dr. Inez Fung, and Dr. Carrie Emanuel. We will now turn things over to Jeff Renner, who is a department alum, was previously the chief meteorologist at King TV, and is involved in a number of local television projects around the Puget Sound area. Thank you.
So I didn't go away entirely. It's a delight to see all of you and some very familiar faces here. I always consider it an honor to be asked to help out in this small way, as I really credit my degree from the University of Washington with enabling me to work more effectively on behalf of the public in my forecast duties that I carried on, well, more years than I'd like to admit to at King TV, not because I didn't enjoy it, but because it identifies just how old I really am. And you get to a certain level and you don't want to admit that. I think it's also really wonderful that the department empowers its graduate students to select a speaker and to organize this series. And let's take a moment at this point to recognize the graduate students in the room. Just raise your hand if you're a grad student here within the department. Let's have a round of applause. You get too little of that. And at the end of a, I'm sure, trying year, definitely am glad to go ahead and recognize you. And I really leaned, and those of us in the public sector as forecasters really lean on the work, some areas more directly than others, in helping us up our ability to forecast the weather and certainly all the other science that you're doing. Do we have any undergrad students here? One hand. Okay. You know, I can still feel your pain, so. And of course, the people that make this the incomparable department it is, the faculty and the staff, if you raise your hands and let's recognize each of you. Although I'm not in the business of formally composing forecasts anymore, though, as I was mentioning earlier, I like to competitively race sailboats, that I get these calls from people saying, okay, can you tell us what you think and what part of the course is the wind going to be strongest on and that sort of thing. I do find that I'm frequently called upon to offer presentations on climate change to general audiences. And that was just one reason I was really excited and very quick to accept the request to host this particular event. In the midst of much misinformation, and I think it's fair to say disinformation, getting clear answers in terms of what we know and what we don't know is of paramount importance right now. We couldn't be hosting a more highly qualified speaker. She serves as senior scientist and head of the climate analytics section, positioned within the Climate and Global Dynamics Division at the National Center for Atmospheric Research in Boulder, Colorado. Our speaker has co-authored over 100 publications, was a recipient of the AMS Meisinger Award, the AMS Editors Award, and is a fellow of both the American Geophysical Union and the American Meteorological Society. And she has strong local roots here. Most of you probably already know that, having earned her PhD in atmospheric science right here. So please welcome Dr. Clara Desser.
Thank you very much, everyone, for coming tonight. And I can't tell you what an honor it is to be asked by the graduate students of the department, my alma mater, to have invited me to come here. It's like one of the highlights of my career. So I appreciate that invitation. And I never thought I would be introduced by Jeff Renner. So anyway. So today I will, in the short time that we have, try to give you some background on how we make climate projections and how we make sense of what climate models are predicting for the future. I thought I could just introduce myself a little bit for those of you who don't know about the National Center for Atmospheric Research, located in a beautiful property up above the city of Boulder. It's sponsored by the National Science Foundation, and it sits below the beautiful, it sits below the beautiful Flatirons in Boulder, sort of an iconic symbol. And it was designed over 50 years ago now by I.M. Pei. This was one of his early projects. He went on to do many, many other things. And he just died a few months ago at the age of 102. And it's such a nice photo of him there. So NCAR is a nexus for university collaboration. It's really a facility designed for the university community. We have about 115 atmospheric science departments who partner with NCAR. We do a lot of workshops and host a lot of graduate students and undergraduate students. There's research aircraft for field campaigns. We, in collaboration with the university colleagues, develop and analyze models of the sun, weather, and climate. So it's a real privilege to work at a place like NCAR and really be part of such a broad community. And it's also nice to be sitting at the base of the Rocky Mountains. You never actually see this view unless you go far enough to the east, but it's a pretty spectacular location. So I'd like to frame my remarks in terms of that we always have to be cognizant of this balance of influences on climate, on our climate system today and in the future, that there are two big influences on the system. One is anthropogenic and one is natural. And the balance of these really very much depends on the location and the time scale and the quantity of interest. And I'll show you some examples of that as we go along. But it's really a balance. It's never one or the other, and they coexist. And even if the natural variability in some cases outweighs the human influence, that does not negate in any way that there is an anthropogenic influence on climate. So the dominant factors under these categories, of course, fossil fuel burning is probably the dominant one, also deforestation, CFCs that led to the ozone hole, aerosols, that's all categorized under anthropogenic forcing. And then the dominant contributors to the natural forcings are, of course, the solar and orbital cycles, volcanic eruptions, and then this category of internal variability, which I'll talk a lot about. And that's processes that are intrinsic to the climate system. The atmosphere, the ocean, the sea ice, the land surface, all combine to produce spontaneously variability, and that pervades the climate system. And it's something we have to be very aware of when we look at the data records. So I'm really going to highlight these two factors. On the left, the impact of fossil fuel burning, and then under the natural influences, the intrinsic variability of the climate system. So of course, we've all seen these iconic images of extreme events that of course cause enormous toll on life and property and cost. And so each one of these is of course a tragic event. And behind these are, again, this twofold impact behind each one of them. So one never asks the question, which is it? It's always, both factors are behind each one of these. So the way I've organized this talk, first I'd like to go through some of the core concepts around global warming, global climate change. Then I'd like to bring us from the global view down to the local view, where you'll see the internal variability rears its head and becomes maybe a confounding issue. And then I'd like to talk about how we use our climate models to make projections for the coming decades, and really that these projections should be thought of as a range of possible outcomes, really a risk, rather than a single answer. So, of course, to do this, I'll introduce these Earth system models, and these are, of course, the cloudy crystal ball. Last time I checked on eBay, they were almost gone, so you got to buy it now. And it's a pretty good price, so I think we should be on our way. So first thing, core concepts of human-induced climate change. I think it's really important to frame, all of the work that depends on climate models to really come back to, the basics, which, of course, underpins global warming. So one, it's based on direct measurements and the laws of physics, the energy balance of the Earth. And that's really at the core of human-induced climate change. So first, we, thanks to Charles David Keeling, we have a beautiful, precise record of carbon dioxide in the atmosphere. He really pioneered these measurements by going to a pristine site in Hawaii here at the top of Mauna Loa, and brought back air samples to his lab at Scripps and conducted, I think, really the first very precise measurements of CO2. So, of course, we all know this iconic graph of the CO2 variations at Mauna Loa, and there's been something like a 30% increase over my lifetime, which is remarkable. And of course, there are shifts in the rate of increase, but overall, it's very striking. And the upward trend is, of course, attributed largely to fossil fuel burning. And then, of course, embedded within that are the seasonal variations, and largely due to the vegetation and its uptake of CO2 during the growing season. So one can also look at this remarkable set of CO2 records, all from, again, these pristine sites around the globe, in this case on a transect going from Alaska all the way down to the South Pole. And they all show, roughly the same increase in the rate, CO2, indicating that this is a well-mixed gas in the atmosphere. And then, of course, very striking, the seasonal variations increase as you go towards the more vegetated northern hemisphere land. So it's a beautiful, beautiful set of measurements that are precisely done. Then in a larger scale context, we can, in air bubbles trapped in the Antarctic ice core record, gives us a very long record of thousands of years of atmospheric CO2. And then at the end, one can append the Keeling curve and get this sort of 50% increase since pre-industrial times. And if this rate of increase continues, we're on track for a doubling of CO2 in about 40 years. So the lifetime of, I'd say, the majority of us in the room. So it's very serious. So secondly, I think we have, very, again, direct measurements that this CO2 increase is due to human activity. And I just simplify it in a schematic way here that, of course, trees, vegetation in general takes up CO2 during photosynthesis, and in general, vegetation tends to favor the lighter isotope of carbon. So this ratio of carbon-12 to 13 is sort of a fingerprint of the woody material. And when that gets buried and becomes what we call fossil fuel, that then retains that signature of the enhanced carbon-12 isotope relative to 13. And then when we burn this buried material, i.e. coal, that's returned to the atmosphere. And we have direct measurements from, again, pristine locations, such as this one in Tasmania, of this increase in the ratio of carbon-12 to 13. And again, that's the fingerprint that it's really directly from our burning of fossil fuels. So third, we know that CO2 is an efficient greenhouse gas. Many people have, of course, contributed to this knowledge. And sometimes it's, I think, lost that Eunice Newton-Foote actually presented some of the first work on this. And later, a few years later, John Tyndall and others made direct laboratory measurements that showed that CO2 is a very powerful greenhouse gas. And then, of course, for those of you who haven't seen this before, the greenhouse effect, just briefly, of course, the Earth is heated by the sun. Most of that solar radiation passes directly through the atmosphere. And then the Earth returns that energy to maintain some radiative equilibrium, and that is in the form of infrared radiation. And the primary absorbers and emitters of infrared radiation are CO2 and water vapor. So those are termed the dominant greenhouse gases and, of course, make our planet habitable. And then, again, many people did sort of energy balance calculations, including Svante Arrhenius, and made sort of simplified energy balance models to calculate, with current knowledge at that time of coal mining and burning our coal, how much the Earth might warm for a doubling of CO2. I recently found out that I'm related to this man. It's my uncle's grandfather, but I hadn't actually put that together until I gave this, preparing this talk. So so of course, because atmospheric CO2 is increasing and it's leading to more energy being trapped within the climate system, there has to be conservation of energy, and so we have to see that manifest in our global records. And one of the most direct ways is that the heat content of the oceans, which of course store the majority of the heat in the climate system. We have very nice records now from ships and buoys, et cetera, that it's a very clear upward trend in the global ocean heat content. And that warming of the oceans then leads to much of this steric rise in sea level. We have shorter measurements. This is from satellite data, but again, very clear manifestation of the greater amounts of energy that are being trapped in the climate system. So that's just sort of the broad brush underpinnings of the science of global warming. So for the second part of the talk, I'd like to bring us from the global scale, which has to obey these large-scale constraints of conservation of energy, and bring us to the local view, which is more nuanced, largely because of the natural variability. So I'd like to introduce that concept. So here, for example, is the global surface temperature record, not the ocean heat content, but these are surface temperature records from land and ocean. And of course, there's ups and downs in any individual year, but this long-term upward trend. This graph goes just through 2015, but of course, we've had a string of record warm years since then. So if we look at the last year on this record, 2015, which globally was at a all-time high, we look at what the U.S. looked like, and it was very polarized. This was during the Obama administration, and for much of the winter, but especially in February, the eastern half really, it was record cold during that time. And then the west here, western half was record warm. So it was a very, obviously divided, but very non-uniform picture. And this was largely due to the displacement of the jet stream. So it was a very amplified jet stream with a high pressure off of the west coast and a low pressure all the way down almost to Florida. And that was very much what brought the heat, record heat to the western states and record cold to the eastern states. And then I know, as all of you know, having come through the winter in Seattle here, and I know for myself in Colorado, this past winter, again, was very cold, especially in the northern tier and southern Canada, and then very warm in the high northern part of Alaska. So again, another sort of dipolar pattern of temperature and very non-uniform. And again, the jet stream was very much behind that kind of pattern that we see. So in general then, conceptually, we can think of the factors that give rise to this internal variability, or I'll call it natural influences on climate. So a very important one is the atmospheric circulation. And this is very chaotic, of course, nonlinear dynamical system, limited predictability. And one always thinks of this as just high frequency, but actually it imprints on much longer timescales, as I'll show you later on. And then, of course, one can bring in another class of intrinsic variability in the climate system, which is due to interactions between the ocean and the atmosphere. And this gives rise to longer timescales of variability with somewhat longer predictability time horizons. But beyond that predictability time, which is typically less than a few years at best, one can still think of this as an unpredictable sort of random sequence that occurs. So some examples, of course, prime examples are El Nino on the year-to-year time scale, and then decadal variability in both the Pacific and the Atlantic that are very much coupled phenomena. So putting this all together, just sort of conceptually, I like to think of it as a roll of the dice. And the dice have, different weights, if you will, and different, it takes a while to roll them maybe for the decadal variability. But once you are beyond the limit of predictability of these phenomena of climate variability, it really is a roll of the dice. It's random, and we cannot predict this ahead of time beyond, weeks to, at best, a few years. And so this is what, when we try to look at the local manifestation of anthropogenic climate change, we always have to be very aware of the influence of these internal processes. And recently I've thought about that this very much has analogy with Stephen Jay Gould's beautiful book, Wonderful Life, on evolution. And in a sense, it's the same thing, and he called it contingency, process by which historical outcomes arise from an unpredictable sequence of antecedent states, so earlier states. And again, it's the roll of the dice. And in fact, so he surmised this by this fossil record in the Burgess Shale. And in fact, we could have been descended from this creature, hallucigenia, as equally probable as what we did arise from. So it's very much, again, that the past is not necessarily the only outcome that we could have gotten. And it's very analogous to our past climate, that it could have unfolded in a different way, and we just happened to get the roll of the dice that we did get. So just to beat it home here, natural and human influences coexist, especially on the local scale, and limited predictability for the internal variability, but can have marked effects. And I'll show you one example from my own work, but Mike Wallace and many other colleagues have done similar work. So this is showing you a map of the linear trend, or think of it as the change in air temperatures over the continent over the last 50 years, roughly. When we did this paper, that was the last 50 years that we had records for. And you see on the left here, that was actually what occurred, and warming everywhere, and especially over Western Canada. And then we've done some calculations where we try to map the natural variability, the influence of El Nino, the influence of the Pacific decadal variability, and jet stream type variability. And we can make estimates of what that would have caused in terms of temperature change over 50 years, and that's what's in the middle map. And then we can remove the natural influence and end up with our estimated anthropogenic influence. And you can see that the pattern, while similar to that of the actual, the amplitudes are quite a bit weaker. And in particular, for this region over Western Canada, our estimate is that roughly half, it's sort of a balance of this scale of roughly half and half. So again, very important to be aware of. So now I'll turn to the main part of my talk here, and that is to talk about how we make projections and how we use our climate models and some of the uncertainties in the models themselves, and then the uncertainties that is due to this superposition of the internal variability. You can drink here. So climate projections. So I sit at NCAR. I was actually trained with Mike Wallace on observations, but made the decision to go to NCAR, where, it's modeling Mecca, and really try to remind myself that models are, just this imperfect tool that we use, but they can still be useful. And there's sort of a fine balance how to interpret them. So Earth system models, these are sort of the newer class of models where we include all these components that are shown here. And typically, they have a spatial resolution of about 4 grid boxes over the state of Washington. So we are not, of course, resolving all the complex topography and land-sea contrast that we have here in Seattle. But we are giving sort of a more, these are useful for looking at larger scales. And these models, of course, are continually being updated, and in the next generation will have much more representation of aerosols and chemistry. Ice sheets are becoming, starting to be put into these models, active carbon cycles that affect the climate, et cetera. So that's sort of on the horizon. And these models, of course, they're based on fundamental physical principles, some of which are listed here. So these we have, of course, very sound knowledge about. And then there are other things that are more empirical, especially in this class of models where we are not resolving a lot of processes that are occurring within a grid cell. So these have to be parameterized in some way, and those parameterizations are one aspect which gives rise to differences amongst models. They treat these parameterized processes in different ways, and so we get different sensitivities. Clouds are, of course, one major parameterized process, and is really underneath or underpins these uncertainties in what's called climate sensitivity of global climate models. There can be a fairly wide range of global temperature response to a doubling of CO2, largely in part to the sensitivity of these parameterized processes. So how, as a community, do we make these projections? It's very much a coordinated effort by the Intergovernmental Panel on Climate Change, and Susan Solomon is here and has spearheaded a lot of this work. And these are coordinated assessment reports that really inform our policy, and reports every 5 to 7 years. There's one that's now in progress that should be out in early 2021. A lot of people involved, lots of climate models, and really underpins a lot of our knowledge, as I said. And then there are interim reports when needed, and for example, for the Paris agreements on this target of 1.5 degree or 2 degree warming, there was a whole special report. So the community, to make valuable scientific use of our climate models, undertakes this common set of experiments, the Coupled Model Intercomparison Project, as it's called, with different CO2 specifications, as well as other well-mixed greenhouse gases. And so we treat, we examine different emissions scenarios, different projections of the future rates of fossil fuel burning. So we carry out experiments for the historical period where we have estimates of these, of the CO2 increase, plus other external effects on the radiative balance, including solar and aerosols and volcanic eruptions. And then for the future, we follow prescription of four different representative concentration pathways. and see how our models respond. So just as a sort of tells you what is behind these RCPs, as they're called. It's a mix of energy usage from these different sources, and each one of these scenarios has a different projection for how much energy is being derived from these different sources. So now I'll walk you through how we actually go from putting in a CO2 emissions into our models and actually getting the climate response. So we begin, as I say, with prescribing a certain rate of increase of CO2, and typically we have these 4 scenarios, as you see here, and they have different times at which we may reduce our emissions to meet certain temperature targets at the end of the century. And then, just like a bathtub, we have to think about that as we are putting CO2 in the atmosphere, even if we reduce the rate at which we put it in, the bathtub's still going to fill. It's just filling more slowly. And so then we can make sense of the actual concentration of CO2 in the atmosphere. So in all of these curves, except the green one, CO2 continues to rise. It just rises more slowly even after we start to reduce our emissions. The only one where it actually starts to go negative is this lower 1.5 degree target. So then, of course, as I showed you at the beginning of the lecture, the amount of energy that's trapped in the system due to this greenhouse gas can be then ascertained from our climate models. So we can go right to this energy unit, watts per meter squared, from the added CO2. So these curves look a lot like the CO2, the cumulative CO2 concentrations themselves. And then finally, one can go from this measure to global temperature. And here, the color scale, I don't know why it's reversed from the radiative forcing, but I've put in here in red, that's the continued growth business as usual forcing, which is sort of around a 5-degree centigrade warming globally by the end of the century. And if we reduce emissions now, this green scenario, we may have a chance to limit our warming something around 1.5 or 2 degrees. So that's just stepping you through the basic physics on a global scale. Now, of course, this is a global number. It sort of doesn't tell you how big the effects are locally. So here I just show you the maps for the end of the century that are associated with these scenarios. And if you look at the Arctic, of course, it warms, more than twice as much as the global mean, even more than that. And land areas tend to warm much more than ocean areas. So that single global number is, not valid, of course, at any given location. And if we look at precipitation at the end of the century, you can see that here there's a mix of areas that get wetter, areas that get drier, and of course this scales very much with the amount of global warming. So this is the human-induced part of climate change. It's not necessarily what we're going to witness as the decades proceed. So I thought I'd tell you a little bit about how we actually vet or evaluate our climate models. There are a whole chapter in the latest IPCC report devoted to this, but I've just highlighted 3 fundamental ways that we try to evaluate these models. The first is that they give a credible simulation of this natural variability. It's a very difficult and uncertain process of evaluating the internal variability, because our observational records are actually quite limited when it comes to evaluating it. But anyway, that's what we try to do. We also ask that the climate model has a realistic simulation of the global temperature record, because that's largely constrained by the cumulative CO2 emissions. And then we also ask that our models have some credibility in terms of reproducing past climate states for which there was large external forcing. And again, I'd like to really emphasize this point about the internal variability, that the climate models need not have a realistic chronology of the internal variability, but it just needs to be realistic in terms of the statistical characteristics. And again, this comes back to this idea of contingency. So just as an example, if we look at El Nino and La Nina behavior, the top curve here is showing you the observed index for El Nino and La Nina, and you see a mix of events. And then I'm showing you on the bottom two curves, two different renditions of the same climate model. And you can see, of course, that the timing of El Nino events doesn't match between the observations and the models, and that the two simulations don't match either. And that's not the point. They don't need to. But overall, the amplitude and the frequency and the power spectrum of the simulated El Nino behavior has to fall within the uncertainty bounds that we have on the observed record. So now I'd like to just tell you how we make these, how we include this idea of contingency or internal variability in our models to get at this combined effect of the anthropogenic forcing. So I use a hammer, that's the big hammer on the system, and then this idea of contingency or the butterfly effect, the fact that these sequences of internal variability can unfold quite randomly, and we can't know ahead of time what it will be like. But we just have to be aware that that introduces uncertainty, or at least a range of outcomes in our projections. So how do we add this idea of contingency, this idea that things could unfold in different ways due to the internal variability? So I'll just show you an example of work that I was involved in, and I loosely call it the 40 Earths project. So we took the community Earth system model, and we applied the historical radiative forcing, applied the same future scenario, business as usual, and then we began each one of these simulations with a round-off error difference in the atmospheric temperature. And we just let the simulations evolve and then analyze the results. So here I'm showing you the first 60 days of all the simulations, and the red curve is just one of these simulations. And you can see that the first 10 days after introducing this round-off error, we have all the simulations follow one another. And that's just the predictability limit for weather. And then there's this very rapid divergence of the global temperature curves, and that's due to now this random chaotic variability that sets in. And if we look now at the full record of these simulations from 1920 to 2100, I'm showing you the global temperature response in the model, and the black curve is the average of all of these 40 Earths, and the gray is showing you each individual one, so you can sort of see the envelope, and then the observed record is in red. So as I said before, one way of vetting our climate models is that we want to ensure that the observed temperature record falls within this, that the model can encompass the observed record, which in this model it does very nicely. So now I'd like to show you, this is again this global view. It's quite simple because it's really based on energy balance considerations. But now let's look at the local view and what happens when we have different renditions of this internal variability that's superimposed upon a common anthropogenic response. So I'm coming back to this example that I showed you at the beginning, looking at North America and looking at the temperature change, the linear change in temperature over the last 50 years. And this time, instead of showing you one map, I have, in this case, I'm showing you, I guess, 28 of the 40, doesn't matter. And so each one of these, you don't have to look at the detail, but each one of these outcomes here is completely consistent with global warming, with anthropogenic climate change. But they look different just because the sequence of the natural variability is different in each one. So you can get a mix of cooling and warming in some, or you can have warming everywhere, and the patterns can be very, very different. So, you know, all we ask is that the real world, if our model is a credible model, that the observed temperature change actually sits somewhere within this range. So if I show you, coming back to the map I showed you earlier, that is the observed temperature record, and it just happens that, you know, simulation number 7 had the roll of the dice that, you know, was very similar to the observed record. So in this case, at least in a qualitative sense, we can say that we have, at least for this metric, a trustworthy model. So once we establish that, then we can look at future changes and have some more confidence in what this model produces. So again, we come to the Earth system model, our proverbial crystal ball. And here I'm showing you from this 40 Earths project, 2 of the possible future changes in wintertime temperatures over North America, sticking with the same example, for the next 50 years. And there is warming everywhere, no doubt, but the amplitude of the warming can vary. And so, for example, you know, I've put Seattle there, but you can, the whole western part of the US, we could have high warming of something like 4 or 5 degrees centigrade, or warming as little as 1 degree centigrade. And that both are completely consistent with the same amount of CO2 increase. So this is not sensitive to, it's only one model. It is one model, the same model for both of these maps. It's the same increase in CO2, and the only reason that these are different is that the roll of the dice of the internal variability differs. Then I can show you precipitation, and again, the next 50 years, and here it's really easy to see the differences. And again, if I highlight Seattle, you can be near zero change on the left, or you can be getting wetter. And if you look in British Columbia, you could have getting drier or getting wetter. So it's a very broad, for this particular example of wintertime temperature changes, if the snowpack, or if you get more rain in Seattle or less rain, you can't use that as evidence for or against anthropogenic climate change. This is all consistent with that effect. So it's useful, I think, then to think about, instead of a single outcome, to really think about the chance or the risk of a certain change. So in this case, I'm showing you the chance of getting more or less rainfall over the next 50 years. So I'll just walk you through the diagram. So this is all based on this 40 Earths project. So it's this this community Earth system model, which we've shown has some credibility, and it's just 40 different possible renditions of the internal variability. So for example, if we look at most of Canada, on average, something like an 85% chance of having wetter winters over the next 50 years. If we look at the West Coast, sort of a 65% chance ballpark number on having drier winters. And then sort of this Midwest area, equal chances. So again, it's this coming back to the balance, the scale of human and natural. And I think that's a useful way maybe to communicate this information. So then, then we're up against, okay, how do we assess if we do something about diminishing our CO2 emissions? How do we assess if it has made a difference? And it's a bit more challenging to do that on the local scale. On the global scale, we know that temperature, we can get it down to maybe 2 degrees instead of 5 degrees. But on the local scale, it's going to be much more challenging to identify the benefits. But of course, there are benefits, but we have to take into account this internal variability. So another project that we had at NCAR was to run another set of simulations with the same model, but a lower emissions, CO2 emissions scenario, this middle of the road 4.5 emissions scenario. And again, running many, many of these realizations of the model. And so then we can make maps such as this one, which I think is a very direct measure actually for communicating this to the public. So this just shows you at each grid box the probability of exceeding the hottest summer on record by 2070. And what I mean by on record is that we take the historical time period, as long as we have observations for. So in this case, we've, I think, gone back to about, 1950 to present, calculated the hottest summer on record, and then that's our threshold. And then we just count up the number of realizations of the model under each one of these scenarios for which the summertime temperature exceeded that historical record. So you see a lot on the high scenario, RCP 8.5 on the left, you see a lot of red, and on average over global land regions, there's an 80% chance of exceeding the hottest summer on record. If we do reduce our emissions to this 4.5 lower emissions scenario, we cut in half this chance of exceeding the record for global land as a whole. So it's very sort of obvious and powerful way, I think, to demonstrate this. But one still has to take into account, this natural variability. So here I'm showing you for the grid box that's centered in southern half of California, showing you these distributions of temperature during this historical period. I misspoke, actually, we went all the way back to 1920. So that's the distribution of summertime temperatures for each year during 1920 to 2015. And in the black are the observations, and in the gray is the model. So the model's doing a beautiful job of simulating, the temperatures over Southern California in the summertime. So again, we have some confidence in the model. And then you see the middle of the road CO2 scenario in blue and the high end in red. And of course, very obvious that the temperatures are going to rise more for the higher CO2 scenario. But there is some overlap, and so if in the future we do get our CO2 emissions down, it could be that we might not identify that as I'm getting a little tongue-tied here, but you can see that we could have, under the high-end scenario, had a temperature increase of about 3 degrees under both scenarios. And so we wouldn't know, actually, if using this particular location, if it did benefit California to actually reduce the emissions. But that's not the point. The point is that we should always expect this kind of range. So I'd like to close then with a final example of these confounding effects of the internal variability. And then one has to be very cognizant of that when we talk about local scale climate change. And this is an example just from a paper that we're still working on, actually. But I just thought it was a nice example to talk about sort of what people really feel, and that is the daily heat extremes. So this is a record of, for the grid box that encompasses the city of Dallas in Texas. What we've done is, again, it's the same 40 Earths project. We just mark with this vertical bar when the daily max temperature exceeds any in the historical record, so anything that we've witnessed to date. And what you can see, these look like barcodes, but what you can see is that, so I'll just walk you through this. So the top one is just one of those 40 realizations or 40 renditions of the climate model moving forward. And this first example happens to be realization number 20. We had 168 occurrences of the daily maximum or daily temperature exceeding the hottest on record. And you can see that it proceeds sort of in a linear fashion, and you have more of these exceedances as you go into the future. But equally, we could end up, according to this model, with this, where there are 519 occurrences. So a lot more heat exceedances. And they kind of cluster at the end. So it's sort of a slow but then very rapid rise in how many days break the record. Or you could end up with this one where we have sort of middle of the road numbers, but it's very punctuated. And you can have decades in, say, the 2060s where no heat records are broken, even though it's under the same influence of the CO2 increase. So again, it's very challenging to communicate this, I think, to the public that we know about this. It's not an uncertainty in terms of our knowledge of the physics. It's uncertainty because we know that the climate system has a lot of variability, and this is how it's manifest on a daily time scale at a particular location, and that's what people are going to feel. So I'd like to end just with some take-home messages on making sense of climate projections. So firstly, that we have very sound theoretical understanding of global warming, and that's very well established, and I tried to cover that in the first part. And then secondly, one has to really understand that going from the global to the local view of climate change is challenging, and it's more nuanced because of the role of internal variability. And again, that's a very important point, I think, to communicate. And finally, that the future, we should expect a range of outcomes, and that we should characterize things in terms of risk rather than a single answer. This is what anthropogenic climate change will do. So thank you very much. Thank you.
Time for some questions and answers. Perhaps about 10 minutes. Who has a question that you'd like to pose?
That's a great question, and that's something that we can actually now address in a robust way with having so many of these simulations with different climate models. And I think it's challenging to identify whether there have been changes in variability in the observed record because we just have sort of a limited sample. But there's evidence from our models and also from theory that we expect for precipitation, that in general it becomes more variable. Droughts become exacerbated, floods become exacerbated. And in terms of temperature, at least as far as I'm aware, I think the biggest signal is actually in the subarctic or Arctic, subarctic regions where as the sea ice melts, we have less incursions of cold air into sort of neighboring regions to the south. And so we actually get a decrease in the variability due to sea ice loss. And I think so far, I think those are the sort of two main signals. Some climate models do show a change in the amplitude of El Nino events, but it's very model dependent, and I don't think we have any real understanding of the processes or what really underlies that. So I don't think that's a well understood aspect.
Another question. Yes.
Fall within the envelope of the prediction.
You mean the excuse me? You mean the absolute value of the temperature? No, I didn't mean to imply that. I think one has to also look at the absolute value. I guess you're right. I probably subtracted that out from the graphs that I showed you. Yeah. No, that's certainly, yes, we want our models to sort of be in the range of the absolute values of temperature on a global scale. Not sure I understood your question.
I was wondering, how do you verify that the model has the right amount of variability?
Yeah.
We only have one
Exactly. And that's, I think, a really ripe for a lot of work in the years ahead. A postdoc who worked with me, Karen McKinnon, I think has made nice headway in that direction, where you can sort of reshuffle or resample the observed record, and actually you can, so for example, you can take the record of El Niños or Atlantic multi-decadal variability and retain the frequency and amplitude properties of the record, but simply change the, just in Fourier space, change the phase, if you will. And then you can regress your data back onto that sort of surrogate time series of these modes. And then for the higher frequency variability, what she's done is to just assume that sort of a 2-year time scale encompasses a lot of the autocorrelation. And then you can just take, at random, select 2-year periods from the record and just append them. And then that can give you sort of this, we call it an observationally based ensemble. And that's, I think, so far that's been, at least what I've seen in the literature, that's been to date the most sort of useful way of trying to grapple with what the observed record could have given us under a different permutation of the internal variability. But I think there's so much more work to be done on that, and I think it's essential also if we're really going to evaluate our models to not just be limited to the one sequence of that nature has given us. Yeah.
Models, and I imagine there are many different models, but do many of them explicitly consider the location of the jet stream?
Yes, yes. So they all, these are models that, especially for the atmosphere and the ocean, the physics behind the location of the jet stream, the location of the ocean currents, that's really well understood. And these models do represent the sort of fluid dynamics that gives rise to those aspects. So yes, these models have variability in the jet stream and the ocean currents that, certainly has a great deal of realism. You're welcome. Thank you.
You talked a lot about variability in the United States.
Yeah. Yes.
Or other places where variability is smaller.
Yeah.
And my understanding of the
Yeah, I agree. Thank you very much. And I do focus on the U.S. just because the audience is typically, but of course that's sort of very myopic, and also it behooves us to consider locations, populations that are particularly vulnerable, such as island nations in the tropics. And Susan is absolutely right that the relative preponderance of natural internal variability in the tropics compared to the anthropogenic climate change is smaller. And so there's less of this sort of, that the outcome is a little bit more certain in the tropics compared. And also along those lines, things that have more thermal or memory, such as sea level rise or ocean heat content, that's going to be subject to less influence from the internal variability. Thanks, Susan. Yeah. Yeah, that's a great question. I don't have a good answer. These global simulations that we have, and these different realizations, they're being used to what's called dynamically downscaling. So they're being used to force the boundaries of much more or high resolution models that resolve a lot of processes that are not resolved here. So I'm happy to point you to some literature on that. Of course, topography, land-sea contrast, et cetera, does have, of course, a big impact on the fine-grained structure of this. But it doesn't, so it can change the structure, but it's driven by this large-scale variability that exists. But yeah, it's going to be fascinating, actually, when we get to the point of running these, more global high-resolution models to see what happens. Yeah. I am not well versed in that at all, so I really don't have a good response. Maybe somebody in the audience does. It's a great question. Yeah. Okay. It is included in these scenarios. Thank you.
I think I saw a hand beginning to emerge. Yes.
Did she give like an uncertainty estimate?
I know.
Quantifying uncertainty in the stone.
I know.
Comment on that historical.
Yeah. The more I read up on it, I'm not sure 4 degrees is actually what he predicted. I think it was more like, I don't even remember. It seems like it's a range. And I think there are other shortcomings of like the amount of CO2 that he used and other things. So I think I'm just using it as sort of, you know, that there are basic physical principles. But of course, you know, there is sensitivity in these models. In fact, the latest generation of the climate model at NCAR has a higher climate sensitivity, I think, of close to 6 degrees centigrade for a doubling of CO2. And I understand it's largely to do with how clouds are treated and cloud aerosol interactions. And it's a whole field to really, you know, understand if that's more realistic or not. Yeah.
One final question.
Thank you. Great. Wow. Wow. I guess I haven't spoken widely to just general audiences at all. And I think, you know, the few sort of public talks that I've given, I think the people who show up are probably, you know, have maybe more knowledge than sort of maybe the people who don't show up. I don't know. So I guess, I don't know. I feel like people get it. I think it helps for me anyway to just show these direct sort of maps. And it's just very clear. And we're not couching things in terms of complicated statistics or, you know, language or jargon. I mean, it's just sort of what we see, and then trying to just walk people through why the local view is just more nuanced and more challenging than the global view. And it doesn't negate, you know, the science underpinning global climate change. So if it warms by 10 degrees, you know, in the next 10 years in Seattle, or cools by 2 degrees, that's all within, I mean, just figuratively speaking, consistent with global climate change. Yep.
Well, let's
You're
offer
welcome.
our thanks to
Oh.
Dr. Desser.
Thank you very much. Thank you. Thank you. Thanks.